Hey everyone, welcome to the ATAR Notes Chemistry 1-2 Unit 2 Head Start lecture. For those of you watching the live stream, welcome. My name is Josh. I'll be in the chat. I've probably already said hello to future Josh, and I'll be there to answer any questions you have. Please use the chat function appropriately and ask any questions that are relevant to this lecture, and I'll get back to you through that chat. Those of you watching the recording later on, welcome. You're welcome to look through that chat. That chat will still be there, and there may be questions that you have already answered there. So that's pretty cool. So just before we start, I'd like to thank our sponsors for today. You'll see that down below in your portal, and I'd like to sort of welcome you all to what is our ATAR Notes lectures. So my name's Josh, and I work for ATAR Notes. ATAR Notes has been around for a very long time. I think it's been around since about 2007, if I'm correct. For me, I was 7 years old then. For a lot of you, you may have only been a couple of years old, 2 or 3. So it's been around for a very long time. They've been providing free resources for a very, very long time. And they're starting to branch out into all new and fun and cool, innovative things these days, which we'll sort of discuss as we go along. Just to note, we have lots of free resources at ATAR Notes. As you can see there, we've got study notes, lectures, discussions, videos, all these sort of things. I use them throughout my year 12 and my year 11. So it's pretty cool that they're still around now. Further to that, we've also got some paid programs as well. So we've got TutorSmart, who I work for personally. So that's where I sort of fit into the ATAR Notes system. It's our tutoring sort of class type initiative. There's one-on-one tutoring and there's group tutoring. There should be some resources down below, as you can see in your portal, to sort of see what it's all about at TutorSmart. We also have our study guides. They've been around for yonks. They're getting updated at the moment, which is pretty cool, especially for chemistry. They've just been updated for 1-2 Chem and the 3-4 chemistry one, I believe. I've seen the draft of it. It should be out very soon for those of you moving into 3-4 next year, as we're in a new study design. And then we also have Ed Unlimited, which is this cool program where you get all of the study guides and you get all of these neat resources and all of these other chemistry exams and question booklets and all of this online. It's sort of like a monthly subscription and you get access to all of that. So nonetheless, let's get kickstarted in. What I've got up just for today and what might help you as well is I've also got up this, which is our chemistry. It's used in 3-4, but it's useful in 1-2 as well. It's your data booklet. You just need to go through the sort of the chemistry VCAR page. May be useful for you, and I hope you'll know what it is at this point. So nonetheless, who am I? My name's Josh, and I've been tutoring for nearly 5 years now. I'm from Bendigo originally, and these are my 2 pets that do live at home with my parents still. So this is Maya, my dog, and Bella, my very overweight cat. One is very young, one is very old. Bella is very old and doesn't do a lot. Maya is far too young for her and has too much energy and is 30 kilos and would squish my cat. Nonetheless, I completed year 12 in 2018, and I achieved a raw 44 in chemistry, which scales up proportionally a lot because chemistry is quite a tough topic. And right now I'm a medical student. I'm taking an honours year at the Victorian Heart Hospital on Monash campus, but beyond that, I've finished 4 years of my medicine degree. I've got 1 year next year, and then I'll be a doctor. Nonetheless, our lecture plan for today is this. So we're going to start off with acid and bases sort of in the first block and then redox chemistry in the second block. Now, these are both part of area of study 1 and a little bit of area of study 2 of unit 2. So what you'll find is that these sort of make up the starting blocks of our sort of start of unit 2. We're not going to go through the whole of unit 2. There's far too much to go through for a 2-hour lecture, but there's enough to go through for just this little period of time. So we're going to have 60 minutes allocated for each, and we will make sure that we sort of get through all of that. What do you need to know? So what's really important is that you know this, and this is the study design, and it's the new one. So it's really important that you select this one here. So when you go to the VCAR website and you go to download it, this is the one that you choose. Why is that? Because as of right now, there is sort of, as you can see, there's sort of the 2 going on, and you've got a transition state at the moment. So it's really important that you stick with this one because this is the one that's going to be relevant for you and you're going to continue to use it through next year and beyond. So really, really important. Make sure you select this study design. The other one is still floating around. This one has some significant changes. This topic in particular has a few small changes, but most of it actually sort of follows on from the old study design. Particularly the redox side of things hasn't changed at all. So you're going to find that redox is all the same as what it used to be. And so if you have some old notes, you're going to find it all the same. But the first sort of acid-base stuff has changed a little bit. There's a few little examples and a few different things they want you to know. So important you sort of know that. So let's jump in. Topic 1, acid-base chemistry. So what are we going to cover? So we're going to cover these sort of 3 main broad topics. Properties of water, so they want you to know everything about water. How does water interact with other things? How does water sort of exist in the earth? How do we sort of recycle and all that sort of stuff with our water? Because we know water is utilized and then it sort of continues in this cycle of being utilized again and then goes down and then gets utilized again. But it is acid-base interaction. So acid and bases is a really key part of water because water is sort of a neutral molecule and we can sort of neutralize things when we have acids and bases and we put them together. And then application. So how does this actually translate to a question? How are you going to have to answer this on an exam? So moving through, let's start off with water. So basics of water, and these are just the basic pieces of information you need to know. So what you're going to find today is the slides are pretty content heavy. There's a lot of writing on the slides. They're not as sort of interactive and, you know, pictures and diagrams, so forth. That's because a lot of acid base is just words on words on words on words. And it is frustrating, but it's just one of those topics that you just need to know. And you just need to know just the basics about. So we're going to go through the basics and try and give you a bit of a brief overview. What I would suggest, don't go and take huge amounts of notes. Don't have your page all filled out. You've got these slides here. Just jot down key things that you think would be important for you to remember. And then you can always come back to these slides because they will be there ready for you to download. So let's start off. Drinking water. So we all drink water. We have to drink water. Sometimes we choose to drink other things, like I'm drinking coffee right now, but we all need to drink water. Drinking water is essentially what is safe for consumption. So the difference between water and drinking water is safe for consumption. Our Australian guidelines say that water needs to be clear, it needs to be aerated, it needs to have no taste or odor, and it needs to be free of chemicals that can cause harm. So the UN has its own sort of guidelines. The Australians sort of build their own guidelines on that. It is a human right. Really important, but it does not mean everyone around the world has access. We do estimate that over 1 billion of the world's population drinks unsafe water, and many have little to no access to water. I'm sure we've all seen videos of it. For those who go to sort of like Catholic high schools, you have like Caritas and stuff, which is a charity that particularly looks into like building sustainable water sources for those countries that don't have access to it. So it is a human right and is something that we need to, you know, make sure people have. So where is the Earth's water? And that's a really cool thing about it is that most of our water is actually in the ocean, and that water is undrinkable, you know, or it's not useful. It's got that much salt in it, and it's really hard to take the salt out of the water. We'll explain why chemically in a little bit. But essentially, most of the water is in the ocean, so it's a bit sort of useless. And then of that stuff that is fresh water and it is useful, 68% of it is found in glaciers. Not really useful again. So again, we're talking about how water is it's actually a very scarce resource, considering 1.2% of it is actually obtainable, and that 1.2% of it is 1.2% of 2.5%. So you're looking at something like 0.02% of all water being accessible. So as you can see, this is where it then is found. It's found in lakes, ground ice. This is all stuff that we can obtain. So this is where the best sort of contribution of water is. So one thing they really want you to know is sort of how you treat water, and they want you to know sort of the basics of the chemistry behind it. So I've sort of broken it up into the 5 steps that you can sort of see on this image here that's taken from the CDC. So this is sort of an American thing, but I've sort of changed it such that it fits what we in Australia do, and what VCAL wants you to know. So we start off with coagulation. So this is where we get our positively charged chemicals and we neutralize the negative compounds dissolved into water. So this is a really important step because water that we obtain usually has lots of these sort of negative compounds from the soil absorbed into it and dissolved into it, and it's just within the solution. It's impossible. You can't filter it out. You can't put it through a filter. It's not going to come out. You need to clump it up to filter it out. So by doing that, by putting these positively charged chemicals in, what they do is they go in and they clump up. So they go into sort of a vial like this, and you got water, and they go in, and then they attract all these other ones to it, and it makes this big clump. Now this big clump can then be filtered out. So next step is what we call fluctuation, and this is gently mixing water with the added chemicals to form what we call our flocks, which are our large particles. So that's this step here. We refer to as fluctuation. Sedimentation, water is given time to allow the flocks to settle at the bottom and the clear water at the surface. So as you can see in this one here, this is sort of what it looks like. We get this sort of sand at the bottom, but it's really just our soil. It's our large chemicals. And then what we do from there is we filter. So by filtering, we remove flocks and sediment that has settled at the bottom, and then lastly, we just disinfect. So disinfecting is sort of putting in safe chlorine and chloramines, which are naturally found in our water anyway, but they act to disinfect any chemicals and any bacteria or anything, viruses or anything that's found in the water that should not really be there and is, harmful to a human if they were to consume it. So, what makes water so special? This is sort of the chemistry side of why water is so special. So, water is found in group 16. Now, let's take a step back. Basics of chemistry would have gone through this in year 10. Also would have gone through this as part of unit 1 a little bit. Where are our groups and all of that? So let's go to our periodic table. And going to your periodic table, you have this, you have this sort of it's sideways, which is a bit frustrating. But we sort of have our groups coming down, and our groups come down our columns. And so water has this superpower where it can form bonds from being polar and it having a really strong dipole. And what we mean by that is that group 16 molecules really, really, really attract to our water molecules. And our group 16 molecules, if you look, fall sort of all down here. So we've got our oxygen, we've got our sulfurs, we've got our selenium, and I can't even say that, tellurium. But these molecules really attract to water, and what they do is they form hydrogen bonds. So this is a hydrogen bond. It forms between, hydrogen atoms and our oxygens, and it allows a really strong bond between water. So H bonding is a special version of dipole-dipole bonding. It's just much stronger because the electronegativity between the oxygen and the hydrogen is a lot stronger. And that forms what we call this partial change. So H2O is a hydride. All hydrides form from group 16 on the periodic table, as we discussed. So as you can see here, these are our hydrides. Now, what's sort of odd about this is we're going down the table here. We're moving down the table. We have oxygen, we have our sulfur, and then we have a selenamine, and then the one that I cannot pronounce. These are all going down the table because if we look here, we go down the table here. So we start with oxygen, sulfur, and moving on. But if we look at our boiling points, which are a really key indicator, they're a strong indicator of what our sort of chemical reactions and our chemical sort of bonding and the strength of our bonding that's going on, it gets stronger, but it starts off really, really strong. So again, why is that? This is where we're talking about our hydrogen bonds. And now I'm sure you've all gone through your hydrogen bonds at some point already. But remember our rule for our hydrogen bonds. So I want everyone to sort of take a step back now and think, what was our rule for hydrogen bonds? Does everyone remember what it was? Our rule was hydrogen must be bonded to 3 different molecules, and that is N, O, or F. And most commonly, it will bond to an oxygen. So in this case here, this forms hydrogen bonds. These all form really strong dipoles. And now these dipoles tend to be stronger than most other dipoles because sort of our electronegative differences. But these dipoles are strong, but they're not as strong as this hydrogen bond. This hydrogen bond is so much stronger. Thus, you need so much more energy to make this molecule into a gas. To break the bonds between our individual hydrogen, our individual water molecules. Now, what sort of bonds are those? They're hydrogen bonds, but what are they? They are intermolecular bonds. Really important to remember our differences between inter and intra. Remember, the intra is like, your intranet. Your intranet is like your Moodle. It's what you use within your school. Internet is between different schools, so it's, it's broader. So inter, between molecules, intra, within molecules. So as you can see here, we have our anomaly, always get that word wrong, and our anomaly is our H2O because of hydrogen bonds. So water is pretty cool because it has this really cool feature that even though all these hydrides are special in themselves because they actually have really decent boiling points, they have pretty high boiling points for these type of molecules, the water has its own individual strength in being a really, really high boiling point. So from there, what else can we learn about water? So the other thing we can learn about water is our specific heat capacity. Now, this is a really common calculation that comes up in our our questions, and it's really the sort of first basic calculation you'll need to do when it comes to water. So the specific heat of a substance, and this is of any substance, is measured of the energy needed to heat 1 gram of the substance by 1 degree. So if you take 1 gram of a substance and you want to heat it by 1 degree, how much energy have I got to put in? Every substance has its own heat capacity, as every substance has its own properties. Water, however, is 4.18. And this is the one you need to know. You don't need to know any other one. What's really important is if a question has another specific heat capacity or it asks for another substance, they will give you the specific heat capacity. Water, they will not. Why is that? Because you'll find as you reach sort of year 12, and you should be receiving this in year 11 as well, if I scroll through and I get down to here and I go to this page here, so this is the numbers are at the top, page 5, and this is chemical relationships and then physical properties and constants and standard values. You notice here, specific heat capacity of water, 4.18. They provide you the value. You are provided the value in all year 12 exams, and you should be provided it in all year 11 exams. It's expected that you know to go to your data booklet and obtain this value from the data booklet. So they won't put the value in the question because you need to go to the data booklet or you need to remember it. So 4.18, the units is don't really need to remember because it doesn't really come up and you never really have to write it down. But in this case, we usually use the joules per gram per Kelvin. Now, Kelvin is another version of degrees. So for those of you who haven't worked with Kelvins before, just as a quick hint, if you're given 25 degrees Celsius and they say we want you to use this in Kelvins, you just add 273. So you add 273 to whatever degrees Celsius value you've got, you've changed it to Kelvins. That'll equal 298 Kelvin. 298 Kelvin is just written as and produced with a capital K at the end as the units. That's really important. You need to know how to convert that. Why is it plus 273? Just for a quick explainer. When we use degrees Celsius, 0 degrees Celsius is the freezing point of water. So this is where water freezes. Or water becomes a solid. So water solidifies. For Kelvin, 0 Kelvin is the coolest temperature possible. It is not physically, chemically possible to get any colder than 0 Kelvin because we know that you cannot get any colder than negative 273 degrees Celsius. Negative 273 degrees Celsius is the coldest temperature possible. Therefore, scientists utilize Kelvins because Kelvins starts from the coldest temperature possible. It's their way of utilizing temperature in chemical reactions. It's sort of a better standard for them. And so it's something that you're going to also have to learn to use. So if you haven't used it before and you didn't understand it, that is what it is. 0 degrees Celsius, water freezes. 0 Kelvin is the coolest temperature. Therefore, at 273 Kelvin, water freezes, or, liquefies, whichever way you're going, forward or back. So this is sort of the freezing point of water. That's 0 degrees Celsius. So that's kelvins. So really important you know that. The other two there you should know. Joules is just energy, grams. And that's sort of how that works there. The other equation that you need to know with this is Q equals mc delta T. Now, this is an equation that we use to link the specific heat capacity to temperature and energy. So this is how we link all these things together, and this is where we use that 4.18 value. So we talked back here that C is 4.18. So generally in this equation, this is going to be 4.18. Now, depends on what they use. They may use something other than water, but they'll give you the value. Usually it'll be water though. So you just need to be prepared that it's usually going to be water. So you're going to have to stick with water most of the time. So as you can see here, Q is the energy absorbed or released. So warning, it's joules, not kilojoules, because we're using 4.18. M is the mass of the substance in grams. Really important, this is not volume. So a lot of the time, what they'll do is they'll say you have 5 liters of water. That's wrong. You cannot put 5 liters in there. Now, why is that? I want everyone to have a quick think. 3, 2, 1. What do you think? Why is 5 liters of water incorrect in that? Because you might say to me, well, isn't that just 5,000 grams? Because it'd be 5 kilograms, so wouldn't it be 5,000 grams? It's actually wrong. They've changed it recently. Well, not that recently anymore. I think it was as of about 2018. This is what we use. We use 0.997. So if I have 5 liters of water, I need to convert that to grams. I'm going to go 5,000 because I want milliliters. 5,000, which is, 5 liters. 5,000 milliliters times by 0.997. So you do 5,000. So we'll do it over here. Times by 0.997. And that will equal, I'm just going to do it quickly on my phone, everyone, because I don't have my calculator next to me, apologies. You do that and you get a value of 4,985 grams. So there is a bit of a difference there. There's 15 grams of difference. It's fairly significant in the context of the question. Therefore, it's really important that you change it. So it must be in grams. The specific heat capacity of water, 4.18. And then delta T is your change in temperature. I don't know why that didn't come over, but nonetheless, delta T equals your change in temperature. So delta means change. For those of you who don't know, delta, which is the triangle there, that means change. So it's a Roman symbol, Latin symbol. It's an old symbol. It's like the alphas, betas, all of those. Delta means change. So change in temperature. Now, what's really cool about this is if they give you the change in degrees Celsius or the change in kelvins, doesn't matter. You can use either. Why is that? Because if I say I went from 25 degrees Celsius to 35 degrees Celsius, that in kelvins would be 298 Kelvin to 308 Kelvin. Is there much of a difference there? There's not. There is 10 degrees Celsius difference or 10 Kelvin difference. So in this case here, you're going to put 10 in no matter what, so you don't need to convert. You just put in 10. You say, all right, this is 10. Because it's going to be the same for kelvins or degrees Celsius. So that's your other equation there. And I think what's best about this is we go through an example. So this is a really good example because they've used something else. They've said the heat capacity of copper, and they've given it to you, 0.39. If Cheyenne wants to heat a bar of copper weighing 202.5 grams by 27 degrees Celsius, how much energy will he need in kilojoules? So we have Q equals mc delta T. We want to find out Q. So what we're going to do is we're going to say Q of copper is essentially what we're working with, is equal to the mass, 202.5 times by 0.39 times by our change. We want to heat it by 27 degrees Celsius. Hasn't told us what we start or what we finish at. It just says we want to heat it by 27. 27 is going to go in there because we don't need to convert to kelvins. 27. So we put that in. We will get an answer of 2,132 point, look, it's 0.33. We're just going to put down our 2 decimal places for now. But what's really important is this is joules. Is my answer correct at this point? It's not. Why is that? Because it's specifically asked for kilojoules. Now, kilojoules is the next step on. It's like grams to kilograms, joules to kilojoules, divide by 1,000. So we're actually going to get an answer of 2.1 kilojoules. That is your answer. 2.1 kilojoules. That is how you go about that question. This is a really good setup for it. Should be 3 lines, plus I've produced what equation I'm going to use at the start. Not necessarily always important to do, but it does look good to write this out at the start because it shows you sort of know what you're going to go and talk about. Very good. So how does this all link in with acid-base chemistry? Because this is part of acid-base. Like the first part of this area study is all about acid-base, but the first few dot points on the study design are like, hey, let's talk about water. And you're a bit like, how does this link in? What is the actual link here? Well, that's because water is a great neutralizer. True water is neither acidic or basic. It sits right in the neutral pH. Now, what is a neutral pH? I'm hoping you know this by now because this was talked a little bit about in Unit 1, but nonetheless, we will talk about it very briefly. pH, it's really a measure of sort of your H pluses. Can also be a measure of sort of your OH minuses, but we generally say it's sort of a measure of H plus. Now, acids and bases mean acidic, basic, they sit on a spectrum. Now, the spectrum sits like this, and in the middle is 7. It's like 7.3 technically, I think, is neutral, but for the sake of chemistry and your level at sort of, high school level, we work with 7. 7 is our neutral. Now, we generally say it breaches out to about 14 and 0, but it is actually possible to go into negatives, and it is possible to go past 14. For the sake of, again, your level at high school chemistry, we talk about 0 and 14 being sort of our endpoints. The closer you get to 0, the more acidic you are. This is acidic. The closer you get to 14, the more basic you are. You might also hear that referred to as alkaline, because alkaline also refers to basic. What's really cool is the closer you get to acidic, the more H pluses you have. The closer you get to basic, the less H pluses you have. Sometimes it's the closer you get to basic, the more OH minuses you have. Nonetheless, we're really talking about H pluses here. The more you have, the more acidic you are. The more you move towards basic, the less you have. 7 is the neutral, and that's where we sit. The body utilizes pHs pretty cool. In a pretty cool way. We sort of have different levels of acidity throughout. So our mouth is, it's a little bit acidic, but it's not like a true acidity. It's just below 7. Our stomach sits at about 2 or 3. It's actually really acidic. And then our intestines, so your food goes through your mouth, a little bit acidic, into your stomach, really acidic, into your intestines, it basics back out and goes to close to 7 again. It's usually about 6.57. So we're neutral, and acidic in the middle. This has got to do with sort of proteins and how our body breaks things down. All a little bit complicated. Most of it is sort of chemistry 3-4 and biology 3-4. So don't worry too much about that. But for now, that's a cool way of thinking about how pH works. So acids and bases operate around the donation and acceptance of H plus ions. You may also refer to H plus ions as protons. This is built around what we refer to as the Bronx-Lowry theory, that acids are proton donors, so that give away H pluses. Bases are proton acceptors. So, as you can see here, we have hydrochloride, which is an acid, and we have water, which is a neutralizer, and the hydrochloride has donated its H plus. We have, in this case here, we actually have some neutralization. So we would probably still be fairly acidic in this environment, but we've actually got some neutralization going on. So a conjunct or a conjugate acid-base pair refers to 2 species that differ by a proton H plus. So For an acid, the conjugate base of the acid is the acid with a proton removed. For a base, the conjugate, for the acid, the conjugate base is the acid with the proton removed. It's because you changed the wording, sorry. And then base, the conjugate acid, is the base with a proton added. So, what do I mean by this? If I consider the dissociation of ethanoic acid, dissociation means that I'm neutralizing it. I've mixed it in with some H+. Sorry, I mixed it in with some H2O, some water. As you've got here, you've got ethanoic acid. Ethanoic acid becomes CH3COO as a negative. Therefore, for this acid here, its conjugate base is this one here. And as you'll see, CH, or ethanoic acid, acts as an acid, and it donates its H plus to the H2O. The H2O acts as a base, even though it's sort of a neutralizer, but it's acting as a base here because it's got a much higher pH. It accepts the H plus from the CH3COOH. Therefore, we have this new molecule, which is a basic species. It can accept a H plus from the CH3COOH, so it's considered a conjugate base. H3O plus is an acidic species. It can donate the H plus to form H2O, so it's considered the conjugate acid. So what we're saying here is that this can go forwards or backwards. We can go forwards towards this, we can go back towards the other way. So we can go this way, or we can come back this way. As you can see, it's got a double arrow to indicate that. And we can go one way or the other. Now, this is a pretty sort of complex concept, but I don't want you to think into too much detail of it. What you really need to know is just the basics, and these are sort of just the basics. This is what you need to know, sort of which are the conjugate sort of pairs, and what are we doing? Are we donating, accepting, etc.? Now, what's really cool here is that we said water neutralizes. So water can actually do both. And water gets this really cool sort of name, which is amphiprotic. I can never say this word properly, so I'm going to butcher it every time. But amphiprotic means the substance can donate or accept protons depending on what they're reacting with. So water can act as an acid or a base depending on the solute present. Monoprotic acids can donate only one proton. So these are all different sort of definitions that you need to know. So amphiprotic is probably the most important. This is the one that we generally refer to water with, because water can act as both an acid or a base. Monoprotic, it means it can donate one proton. That's a monoprotic acid. Polyprotic acids can donate more than one proton. Now, what's really cool about this is we also refer to this as bases. I've just used acids as the exemplar here, but you could say a monoprotic base. Now, a monoprotic base can only accept one proton. A polyprotic base can accept more than one proton. Diprotic acids can donate two protons, so a diprotic base can accept two protons. A triprotic acid can donate three protons, so a diprotic base can accept three protons. As an acid loses protons, it becomes harder and harder for it to lose more protons. Same thing happens with bases. The more a base accepts protons, the harder it becomes for it to accept another proton. The third ionization in a triprotic acid occurs to only a very small extent, so it only occurs in some substances, and it's very, very rare. So, acid bases, we need to know sort of what's strong and what's weak. So, strong acids are acids that readily donate protons. And so these are the ones that are more likely to be able to go to something like triprotic. So if it's possible for a strong acid to go to something like a triprotic, it's more likely to get there because it's more likely to keep donating. That doesn't necessarily mean they're all going to do that, because some of them are not possible. They don't have the ability, their molecular makeup doesn't allow them to donate three. So an example of that is HCl. HCl is a strong acid, but it only has one hydrogen, so it's monoprotic because it can only donate one. There's no way it can donate two because it doesn't have two to donate, or three. It doesn't have three to donate, it only has one. So as you can see here, HCl, HNO3, H2SO4. Strong bases are bases that readily accept protons. Exactly the same concept, but the other way around, because they accept NaOH, KOH, etc. For example, this means when HCl donates into the solution, it ionizes completely, leaving only H3O and Cl ions. Now, that's another concept that can be quite confusing. So let's just take a step back. When we put HCl in water, it dissociates. Now, dissociates means that it donates its hydrogen away. It gets neutralized by the water. What we mean by ionizes completely. Now, this is where things get a little bit confusing. Strong acids and bases are more likely to ionize completely. What does that mean? It means it completely, all of it, or close to 100% of the HCl that's in the solution will lose its hydrogen, and it will therefore have a completely neutral solution. Most of it will. When you have a weak acid, less of it does, because less of it needs to lose its hydrogen to neutralize the solution back to 7. Because if we think about it in sort of our terms of our spectrum, so if I make this 7, a strong acid, and this is 0, a strong acid sits somewhere here. These are your strong acids. Your weak acid sits somewhere here. So this is really sitting in this, 1 to 3. And this is sitting in this, 4 to 6. Like, that's not perfect. It may necessarily sit somewhere else. This isn't a perfect example, but what I'm trying to say here is that for this to get neutralized, nearly all of it needs to lose its hydrogen. Nearly all of it needs to be created into Cl-. For this to be neutralized, less of it needs to, because once you lose a couple of them, you've nearly reached 7, and then you're like, all right, I'm cool, I'm happy, I'm at neutral. So strong acids and bases will ionize completely. And if I look at this, it goes like this, and as you can see, I would say this is about 99%, and this is about 1%. So 1% of it stays here, 99% goes here. If this was a weak acid, and we're using a different example, I would say this might be, this might be 50%. And this might be 50%. It might even be that this is, 2%, and this is 98%. All of them differ slightly. But what I'm trying to say is that in these cases here, what you find is that when it's a stronger acid or base, it's going to ionize completely. And that is where all of it, or most of it, is broken down. And therefore we get back to our neutral. This is usually represented as an irreversible arrow to show that the reaction is complete. So even though the reactions can sort of go forward and backwards like we talked about before, when it is a strong acid or base, we tend to use a single arrow because it shows that the reaction is complete. It shows that reaction is, all of it, or all of it has converted over to our products. We're trying to sort of emphasize to the reader and to the examiner that we know that. So weak acids and bases, these undergo only partial ionization, and then weak bases, as you can see here, they are bases that do not accept protons readily. So weak acids and bases. What's really important is you need to know one example for each of these. So you need to know an example for a strong acid, an example for a strong base, an example for a weak acid, an example for a weak base. You need to remember one for each. Really important. For example, this means that our ethanoic acid, which we've already talked about, dissociates into solution. It only ionizes partially, leaving mostly CH3, or our ethanoic acid, and a small amount of our H3O plus and our CH3COO minus. These are represented using a reversible arrow because we want to say, hey, there's actually not that much that has moved across. In this case here, we could say, it's like 5% and 95%. Or it could be like 50-50. You're not going to be given the values, and the values are not necessarily important. It's just important to understand that this isn't going to go nearly as far across. We're not going to get as much moving into that products. So as you can see here, this is a really cool diagram that just shows, your strong acids and then your strong bases, and sort of how they sort of match with each other, because these are all like our conjugate pairs. So our HCl is a really strong acid, but Cl minus is actually a really weak base. Whereas CH4 is a really weak acid, but CH3 negative is a really, really strong base. So you can see sort of conjugate pairing there. So the stronger an acid is, the weaker is its conjugate base. The stronger a base is, the weaker its conjugate acid. Cool. All Right, moving forward. The next thing that you need to know is sort of how to measure acidity. So when we measure acidity, what's really important is that we understand that water molecules can react with itself to a small extent, and therefore it's possible for water to ionize itself. So we get this weird sort of concept where, hey, if you have lots of water, you actually have, so if you have like a glass of water, so I've got a glass of water here. In this glass of water, there's going to be lots of this. There's also going to be lots of this. Like, all right, lots is probably an overstatement. There's not going to be lots of our products there, but there will be some of it because water can actually ionize itself. It's one of those weird things that just happens in chemistry. But we also know that water is neutral, pH of 7. In pure water at 25 degrees, the concentration of H3O plus is so small. What that means there is it's 0.0, so 0.0000007, 0.1. Why did I put 7? 1. 1 molar. That's how small the concentration is. It's tiny. There is like nothing of it in there. Same thing over here. The concentration of our OH minus is the same. It is so small. There is nothing in there. It's such a small amount. That's why I said, like, retract my comment. There actually isn't that much of that, but it's just saying that there is some of both. There is the ability for water to actually do a little bit of sort of pairing on itself. And now what's really cool here is that you just choose one of the waters to be the acid, one to be the base, and then you say, all right, that's its conjugate acid, that's its conjugate base. And that's sort of how we look at our conjugate acids and our conjugate bases with water. There's a few equations that are really important when we talk about our sort of our concentrations of acids and bases. So the concentration of acids and bases is usually expressed in moles per liter, or what we say is big M, or molar. This is referred to molar. So when we say molar concentration, that is that. And we refer to it as big M, but we say molar concentration. Yeah, I don't want you to say big M, but that's what we write, big uppercase M. And this is known as molar concentration or molarity. This is the formula. I sort of like to write it as N equals CV, but C equals N over V is the exact same thing. It's just the algebra way of, editing it. But N equals CV, that's how you go about it. C equals N over V. And that's a really, really important a really, really important formula because that gives you molar, because it's moles over liters. So moles over liters, and that gives you that. So it's really important that you know how to do that. So where concentration is mole over liters, N is moles, V is liters. Acids can also be diluted by mixing with water, and the change in concentration is determined by C1 V1 equals C2 V2. Now, what do I mean by all of these numbers? C1 V1, so C equals your concentration, V equals your volume. What this means is that initially, so if I've got an acid, and let's just say I've got HCl, and HCl is in a mixture of, it's in a mixture of 1 liter and it's 1 molar. So I have 1 molar concentration HCl and I've got 1 liter of it. So I've got 1 times 1. And then what happens is I add in another liter of water. I add in a second liter, but I added of water. What happens is I don't know concentration, but I have 2 liters of whatever it is. So I've got X, because I don't know what it is, times 2. And that's just simply how you go about this. So 1 times 1 is 1. I divide everything by 2 to get the 2 over the other side, and I get X equals 1 over 2, which is, concentration of HCl, 2 is equal to 0.5 big M. That's meant to be a big M. So that is how you go about that. This obviously gets far more complex when you use different numbers. I've just used very simple numbers here to make a very simple sort of equation and show you how that works. So what's really important in these ones is it has to be the same original solution that you've added something into. You can't just get a new solution and say, oh, what's the concentration here? That's a new solution. You can't use this. These has to be of the same solution, and then you sort of add in things or add in water to sort of dilute it, or remove water to, concentrate it. So, getting rid of my scribbles here because there's a little bit more writing. C1 and C2 are the initial concentrations and volumes, and then C1, C2, V2 are the after dilution. So, moving forward. Coming back, sorry, I went too far. What is the pH of the solution resulting from the dissolution of 3 grams of HCl into 150 ml of water? So we have HCl. Some reason they're given to us as a gas. We're going to say this is actually aqueous. And we dilute it into 150 ml of water. What is the pH? Now, we haven't been through the pH formula. It's sort of expected knowledge from sort of the first semester, so your first, your unit 1, and it's also sort of assumed from like year 10, but it's sort of a weird one because we don't use it in year 12, so that's why I haven't gone over it in big detail. We are going to use it in this question, but for the sake of it, what's really cool and important about this is that you don't need it in year 12. So if you're really struggling with it, it's not a big deal because it's not a huge part of year 11 and it's not even in year 12. But we're going to go through it in this question nonetheless. So, if you do want to have a go at this question before I go through it, please pause the video now. Those watching the live stream, obviously don't get the choice in that. For those watching the recording, please feel free to pause it, have a go at this question before I go through it, because I'm going to go through it in 3, 2, 1. Let's go through this. So, 2 formulas you need are, as we discussed, the pH formula, which I hope you all know, but if you don't, that's okay. It's negative log 10 of the concentration of H+, and we need our C equals N over V, or our N equals CV, and that's what we're going to work with here. We're also probably going to need, looking at this, our N equals our mass over our molar mass. I hope you all remember that equation as well from Unit 1. So, first of all, we need to find the moles of what we've got, because we've got 3 grams of HCl, but we don't know what that is in moles. So we need to figure out what that is in moles. We're going to use this formula here. So we're going to say N of HCl is equal to 3 over, now, molar mass of HCl is, H is 1, Cl is 35.5. You can get that from your data booklet if you scroll up to your periodic table. My computer's a little bit laggy because when you have so many things open, it struggles. But as you can see here, you want to find it in here. So HCl is going to be 35.5. I think it'll be back down. No, it's up this end. I always forget where Cl is. 35.5, correct. There it is. So that's what we're going to work with for this one. So 1 plus 35.5 is 36.5, which is going to equal 0.0821 mole. As you can see, I've done this question beforehand just to be prepared. So I've got my little notes on the side with the answers. From here, I then want to find out my volume. So I want to say, all right, I want to find out my concentration because I have my volume as 150 ml, which will be 0.15, and I have my moles. So I found my concentration of HCl is going to be 0.0821 divided by 0.15, and that is equal to 0.547 moles. So 0.547, molar. Don't know why I said moles. Molar. So 0.547 molar. And then from there, what I need to say is, all right, what is my concentration of H pluses? So what's really important about this is it's a little bit of cool chemistry here, and this is a really good tip that you're going to use throughout year 11 and throughout year 12, is that my concentration of H plus within this, because H plus is this part in here, is going to be the ratio of it. So in this case, if I had H2SO4 and I had this same value, my concentration would be 2 times that value there. Would be 2 times it, because I've got 2 of these. However, in this one, I've only got 1 of these. So having 1, what I'm going to say is that my concentration is the same. It's going to be 0.547 molar. Therefore, what I go and do is I go and put this in this pH equation. So I put it in there and I get a pH of approximately 0.26. Now this needs to be done in the calculator. I've already done the answer beforehand. The answer is 0.26. So your pH is 0.26. Hopefully that answers any questions with that one. If there are any lingering questions from this question here, please ask it in the live chat. And if you're watching the recording, please feel free to look through the live chat and see if the question you had is there. Now, last probably 3 slides on this topic, and then we move into redox, which is really sort of the bulk of this area of study, and it's what we really want to get into. First of all is acid-base chemistry. So general formula. So general formula is just like saying, all right, if I have this plus this, not looking at the specifics, if I have, you know, a weak acid and a strong base, what does the formula look like? What is it going to look like? Without the specifics of what we're actually using, what's it going to look like? So there are 4 main ones they want you to know, and we will go through each of them. So the first one is acids and metal hydroxides. So metal hydroxides are a metal with an OH or a metal with a H. So they are hydroxides. We've already talked about these before. Hydrides have H, so this is not hydrides. Hydroxides have OH, so it's metals with an OH. So acids with an OH. What this is going to look like, and I'm going to write it out by words. It is an acid plus a metal hydroxide goes to a salt plus water. Now, what does that mean? What it means, a salt is our metal with a non-metal. So in this case here, let's do HCl plus NaOH. Now, NaOH is an acid, is a base, and HCl is an acid. So, and it's a hydroxide because it's got an OH in there. If I go to this, it's going to go to a salt. So a salt is a metal plus a non-metal. So metal plus a non-metal, I've highlighted the ones there. It's going to be NaCl plus here, this plus this. What does this make us? We've already written it up here, but it's going to give us water. So that's our first one there. Moving on to our second one. Acids plus metal carbonates. Now I'm going to use a different color just so that I don't overlap these. Acids and metal carbonates. Now, metal carbonates are the same thing as above metal, but instead of OH, it's going to be a carbonate is like a CO. And you'll see what we talk about with that. It's like a CO2, CO3. So in this case here, what do we think is going to come out if we've got an acid plus a metal carbonate, and metal carbonates have like your CO2, CO3s in there? Well, pretty obviously it's going to give me, again, a salt, again, a water, but then our extra little thing that's coming out is a carbon dioxide. So again, we'll do an example. So an example of this again is HCl plus, we're going to go Na, I think it's 2CO3. So what does this form? Again, a salt, we discussed, we're going to use the same one as above, a water, and then what do we have left? Because we've used one of these, so we're now at 2, we've used this, we've used this, we've used this. What have we got left? We've got 2 CO2s. So it's going to be CO2. And I should have produced this as H2O, apologies. Then we just need to balance out this equation because it's not perfectly balanced. In balancing out this equation, I'm going to need 2 of this. By having 2 of this, I'm going to need 2 of this. And then that's all balanced out. And that's how you go about that question there. So, important you balance out your equations there as well. The next one that you need to know is acids plus metal hydrogen carbonates. So, same thing as this, except there's a hydrogen in there as well. So, a really good example of this, and we'll use another color again, is the same as right here. Na, but instead of 2, it goes HCO3. So that's a really good example of it. Again, we'll use HCl because HCl is just quite easy to use. What's that going to form? Again, let's have a look. We have a metal, we have an acid, we have a hydrogen carbonate as well. Well, we're going to form, as per usual, our salt. We're always going to form our salt. We're nearly always going to produce a water. So we'll produce a water again. But there's still a carbonate. So we'll probably produce a carbon dioxide. Will we produce anything else? Will it be any different? It's actually not going to be any different, because what we see here is that we don't need to do any sort of balancing because we've got this extra hydrogen. So in having the extra hydrogen there, we sort of have less balancing to do, if any balancing. So therefore it just makes it a lot easier. So NaCl plus H2O plus CO2. No balancing required. Perfect. Our last one here is acids plus reactive metals. Now, reactive metals are things like magnesium, for example, and they're just a solid. So it looks a bit like this. So it looks like, HCl, and then you're adding in just a straight metal. Now, when you have an acid on a metal, so I put solid there because I'm saying it's just like a straight metal. If you add like a metal into an acid, what does it do? It sort of dissolves and disappears. But we've all seen videos of it. When you put a metal in an acid, what happens to the acid? What do we see the acid do specifically? Just everyone have a quick think, take 5 seconds. What do you see the acid do? You see the acid bubble. So when the acid bubbles, what do we think is coming out? Because there's no oxygen here, so we actually cannot produce water. What do we think is happening? Well, we need to get rid of these hydrogens somehow. So what's the best way to get rid of it? Hydrogen gas. So once again, we're going to produce a salt as per usual, but there's no way of making water here. So what's the next best thing we can make? Hydrogen gas. So HCl plus magnesium goes like this. So we're going to have MgCl, and then what we're going to have, and it's also going to be Cl2 because I think Mg is magnesium is +2, and then we're going to have H2 gas. And looking at that, we have 2 of these and 2 of these. Well, we're going to need to put 2 out the front here, and we're all balanced. So these are general formula. The wording is the general formula, really important. The examples we've done here are not the general formula. The general formula is the acid plus whatever we've added in goes to da 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 da. Now I've made these little, whoops, getting rid of that because I accidentally moved the whole screen. I've made these pluses. So that's how that works there. Hopefully that all sort of makes sense in terms of just general formula, and then you can see the examples we've done there sort of solidify what we've done. Now, one last little quick concept before we move into our redox is acid-base application. So I did promise we'd go through a little bit of application. This is sort of the main one they want you to know. There's a few other examples on the study design. You're welcome to look at those yourself. I'm sure your teacher will go through them. But for the sake of our 2 hours, we're only going to go through the one. So the first one they want you to know about, and the most important one they want you to know about, is sort of how does carbon dioxide interact with water, and then how does that sort of, where does that go? What comes of that? So when carbon dioxide is in the atmosphere, which it's always in the atmosphere, it's slightly soluble in water. So as you can see here, we have CO2, gas goes to CO2 aqueous. Now, some carbon in the atmosphere and in seawater reacts to form carbonic acid. So when you've got CO2 that's been absorbed into water, it reacts with the neutralizing water and it produces carbonic acid. Now, carbonic acid is diprotic and ionizes in 2 steps to form hydrogen carbonate ions and carbonate ions, as you can see here. So these are all just steps. So essentially, carbon gets absorbed into water, reacts with water and forms this, and then the water goes, I don't like this, and tries to neutralize it. And in neutralizing it, it forms these 2 molecules. And it happens in 2 steps because we can do it twice because it is diprotic. These both increase the concentration of hydrogen or hydronium ions and increasing the ocean and rain acidity. So the water overall is a little bit more acidic because of this whole process. So it's important to understand that rain is therefore naturally acidic because there's lots of CO2 in the atmosphere, and therefore the ocean is slightly acidic, and therefore the water that is absorbed by, you know, the atmosphere into the clouds, and then further reacting with carbon dioxide in the atmosphere, because it's already in the atmosphere, like we're already in the clouds now, we're in the atmosphere, further sort of acidifies our rain, and therefore our rain is actually slightly acidic. It's at about 5.6. This is very different from what we sort of think of acid rain. So rain is acidic. Acid rain is a different concept. Acid rain is when we become overly acidic. Now, acid rain doesn't actually meet that sort of stereotypical melting everything rain. It's usually not that bad. But as you can, I'm sure you've seen in either movies or TV shows, or you've read through a book, they say like acid rain sort of burns and melts everything. And, you know, it's generally like the horror movies, the things that I don't love. But that's a very sort of stereotypical, over the top way of looking at acid rain. But rain acidity is just normal rain is slightly acidic. So why is rain acidic? As we discussed, CO2 is soluble in water. This happens readily in the atmosphere when the water is absorbed into the atmosphere, and you get this slight acidity forming. This is a natural process, and it's actually necessary for a couple of reasons, and it's why you need to be able to discuss this in an exam question. Why did, you know, Earth, the way Earth formed, why has it allowed rain to become sort of acidic? Because we know the Earth's been around for a very long time, and in times where it's needed to manipulate things like, you know, our ozone layer decreasing, it's changed the way our property of our atmosphere is to sort of fix that ozone layer. Same thing happens with when the rain is acidic. Why is it not sort of just neutralize that and figured out a way to do it? It's because it's necessary. Acidic rain is necessary to sort of form land erosion. We need that to sort of form our rivers, to form our lakes. You know, it forms caves for shelters and underground caves for runoff. It maintains the nitrogen cycle in the atmosphere. You don't need to know too much about this, but it's a really cool point to say, like, nitrogen's the most common molecule in the atmosphere, and we would be overwhelmed by too much nitrogen if it wasn't for the acidity. It actually neutralizes works to sort of maintain the levels of nitrogen and that cycle within the atmosphere. So acid rain is actually, or rain acidity, not acid rain, rain acidity is actually a really common, and it's a really important process that we have to be slightly acidic. Acid rain, on the other hand, is a different concept. It's the concept where things go overboard. We have too much acid, we have too much acidity in the rain, and then we get that sort of more dangerous type of rain. So that is everything for acids and bases. There is slightly more to that topic. There are more sort of little concepts and niche little things you need to know, but for the sake of time, that is a good overview of it. And that should sort of answer any sort of broad questions about what we talk about in terms of our water and our acid bases. So we're going to move into redox chem. This is super duper duper high yield in terms of, this is like a whole topic in year 12. It's not even like a whole topic, it is a whole topic in year 12. You need to know how to do this really well, and they expect this stuff as basic knowledge going into year 12. So it's really important you know this stuff. So we're going to go through the basics today. We're not going to go through anything difficult. Now, redox can become really difficult, and I'll preface that in terms of the first time you learn redox, it's really difficult. So this may be the first time you're seeing it. If it's the first time you're seeing it, you may really struggle with it today. Don't expect to come out of it, you know, knowing everything and being able to answer every single question that comes up. That's not necessarily going to happen. You just need to be aware that this can be quite difficult to sort of get your head around the first time. So what is redox? Well, it's a huge topic, super confusing. Many of you watching this lecture will have never touched it, so don't expect to be experts after today. We're going to move really slowly, and we're only going to cover the basics. We're not going to go into any sort of application-based stuff. That's going to be sort of left for the next set of lectures in sort of our spring lectures, because that'll be on the end of you guys already doing redox, so we're going to go through some really complex sort of application of it. Whereas today we just want to do the basics. The goal today is for you to have a small understanding of the basics, so when you go through in class again, it'll be easier to sort of put that jigsaw together. When your teacher's going through stuff and you're going through concepts, you'll be like, oh, I've heard of that before, I've seen that before, I know sort of how to link those topics together, etc. So redox is basically a concept that involves the transfer of electrons. It's kind of like how we transfer money. Redox involves transferring electrons. Electrons are like the currency of our molecules. So red means reduction, ox means oxidation. These are the two key things that happen. We have reduction and oxidation. Without them, we don't have a redox equation. So cellular respiration to give you energy is an oxidation reaction. Combustion to keep you warm, or combustion, for your petrol in your car, redox reaction. Batteries in your phone, redox reactions. This is important for 3 and 4 chemistry. So all of these concepts can either happen in a direct or indirect way. As you can see here, this color changing is a direct reaction, and this is a redox reaction. So aqueous redox reactions, such as the traffic light reaction, often involve color change. And this is an example of a direct redox reaction. So, I don't know why the transitions went a bit weird there. That was my bad. I think I tried to put animations in that went a bit skew-if. Nonetheless, this is the basic building block of redox chemistry. Redox chemistry occurs in 2 parts, but the 2 parts must happen at the same time. Without one part, the other part doesn't happen. Full stop. If you don't have reduction, you don't have oxidation. Full stop. So, reduction and oxidation can be simplified down into what we refer to as oil rig. Oxidation involves loss. Oxidation involves loss. What does it lose? It loses electrons because they are the currency. Oxidation involves loss. Rig. Reduction involves gain. Reduction involves gain of electrons because, again, that's our currency. So as you can see here, here's some very brief general formula. So you have M, which is your original product, goes to, or comes back from, but we say it's going to go to because we're doing oxidation. So we're going to M plus, or M positive, plus an electron. What that means is the electron is lost. This electron can go wherever it wants now. It's free to do whatever it wants and leave. In our other equation here, so in our reduction equation, our electron has been free to do whatever it wants, and then it comes in here. Free to whatever it wants, and then it comes in here. And now, when it comes in here, it's now added into this molecule, and it's stuck in there. It's not free to go and do whatever it wants. So it's being gained. That electron has been gained. This electron has been lost. Left electron here, this one over here, has been lost. This electron here has been gained. So think of it like this. You've got A plus B. A's got an electron hanging around. They all do, but let's just got an electron hanging around. And then it goes, you know what? Maybe I will. Oh, I don't know why. Again, I think my animations are going a bit skew-if. That electron is going to go whoop, and go over here. So as you can see, these electrons move from one to the other, and they move across, and they make this A plus and B minus. As you can see, I think it was meant to in this. There was meant to be a transition for that to move, but it didn't move. So the electron moves across to our B minus. So the electron was lost from here, and A underwent oxidation. The electron was gained here, so B underwent reduction. Now, this is where the terminology gets really confusing, and you're going to take a few times to get your head around this, so don't expect to get your head around it straight away. Since A sent an electron to B and underwent oxidation itself, we call it the reductant, because it caused B to go through reduction. By sending that electron, it caused B to undergo reduction. Think of it as like the teacher teaches you. As much as the teacher, we call the teacher, but she's not taught, she's teaching you, or he is teaching you. Same thing here. It is sending the electron to B, and as such, when it sends the electron to B, it causes reduction. And so we call it the reductant, even though itself is undergoing oxidation. For B, we think that B pulled the electron. So we're saying B actually pulled the electron from A, and even though B itself underwent reduction because it gained that electron, it caused A to undergo oxidation by removing that electron from it. So we call B the oxidant. So this may be a better way of sort of seeing it. You'll notice in older exams they use oxidizing agent and reducing agent. It's old terminology, but it's still acceptable to be used. The oxidant is the species that causes oxidation, but is itself reduced. I think but is a better word there because it sort of splits up these sentences really well. The reductant is the species that causes reduction, but is itself oxidized. That's really, really important. So the reductant is the species, and oxidation is the process that the reductant undergoes. So remember this like this. I don't remember it like that, but here's a little one that I know one of the other tutors uses. So I have been handing it out to my students for years. Some of them have found it really useful, but oxidant undergoes reduction, reductant is oxidized. You're welcome to utilize that if you want. I just find that it's easier to just sort of remember it and just say, hey, the oxidant causes oxidation, but is itself reduced. So the other cool thing about sort of our redox reactions is that one does not happen without the other. That's really, really important. You cannot have reduction without oxidation, and you cannot have oxidation without reduction. And I want to continue to stress that. Reduction does not occur without oxidation. Oxidation does not occur without reduction. Reduction and oxidation will always occur together. You cannot have one without the other. Really, really important. Now, how do I identify that oxidation and reduction are occurring? Because I know electrons are moving, but how do I identify that? So, the way that you identify that is through what we call oxidation numbers. So, oxidation numbers may also be called oxidation states. So these are used to determine if a reaction is redox. Think of oxidation states as imaginary charges, and we assign them to atoms in compounds. So this is where things get a little bit more complicated. There are a few rules. I'll go through the rules and then I'll show you how we apply those in sort of the question. So first step here, oxidation states of free elements. So Fe solid, that's a metal, sodium solid, chlorine gas, helium gas. These are all zero. These have no charge. They're free elements. They're not an ion. Therefore, they have no charge. They are zero. They are to zero. Oxidation states of simple ions, so Na positive, Cl minus, Mg2 plus, nitrogen 3 minus. These are equal to the charge of the ion. So Na plus has got an oxidation state of +1. Cl minus has got an oxidation state of -1. So these are sort of as they would be. In compounds, again, a little bit different. So in compounds, we have the main group metals have oxidation states equal to the charge of their ions, so Na plus Cl, and then Na will be Na plus, and then Cl will be Cl minus, so we're going to have +1 and -1. We have magnesium bromide. Bromide is -1, magnesium is +2, so we're going to have +2 for our magnesium, and bromide's going to be -1. So even though overall this thing doesn't have a charge, we're thinking about it, there's 2 ions in there. Hydrogen is almost always +1, and oxygen is almost always -2. Now, there is one example. I lie. There are multiple examples of hydrogen and multiple examples of oxygen that are not -2 or +1. However, they never come up. There's only one example that ever comes up in exams for hydrogen. There is no examples for oxygen that, actually no, that's a lie, it's the other way around. There are no examples for hydrogen that have or ever really come up. Oxygen has one example that comes up quite frequently where oxygen is not -2. So that's why we say hydrogen is almost always +1 and oxygen is almost always -2, because the examples that there are very infrequently or never used. But there is one example for oxygen that is frequently used. So the example is H2O2. Now, those of you who know what that molecule is, it's hydrogen peroxide. And for those of you who have heard of that before and are going, oh, where have I heard of that before? Think of like, you've probably watched like a World War II movie, and they typically portray it as sort of the Nazi spies, but it did happen on both sides, would have a hydrogen peroxide capsule put in them, put into their cheek, and then if they were ever captured, or it was usually put into a tooth, they would then break the tooth that would, disperse into their mouth and they would die pretty quickly. So hydrogen peroxide is a really, really deadly poison. It's not necessarily used as a poison. It is very deadly to humans unless we say it is a poison. In this case here, +1, -1. So overall, there's two of them, so it's +2, and you've got 2 oxygens, so it's -2, and they equal 0. But the individual oxygens in there are actually -1. It's one of the few examples you need to know, but you do need to know it. It does come up, so it's something you do need to know, and it's something I do want you all to sort of apply in your everyday sort of chemistry, that this one does come up, and remember it does. Otherwise, oxygen is always -2, and hydrogen is always +1. Sum of all the oxidation states must equal the charge of the species. So let's look at an example. We'll talk about an example that we've been through already, is that we went through earlier. We went through H3O+. Remember, we were working with this with our acids. We were talking about this all the time. Remember that this is always +1 and this is always -2. So overall, I've got +3 and I've got -2, and that equals +1. Well, it makes sense because my charge is +1. So that's sort of how I figure out what's going on. Now, in this one, we already knew that oxygen had to be -2 and hydrogen had to be +1. So it's pretty easy because we already knew that. If you didn't know it, you can then utilize that to figure out what's going on. So CO2, we have -2 for our oxygen. We're pretty comfortable with that. We know it's always -2. So overall, I have -4. Overall, this molecule is 0. So knowing that I have 0 and I've had -4 already because I've got 2 of those -2s means that this carbon needs to be +4. And there's only 1 of them, so the carbon itself is going to be +4. So I've now gone and figured out my oxidation states of all of my individual atoms just by simply knowing that overall my charge is 0. I have -2 for my oxygen, so therefore I'm going to have -4 for my 2 oxygens. And therefore, my +4s there, as you can see, there's only 1 carbon, so it's going to be +4. So that's sort of how you go about that one there. If I rub out my workings, I believe there should be already workings there. As you can see, it does it for me. It's a little bit laggy on my screen, I do apologize, but it will pop up eventually. So, moving forward, I don't know why this is full lagged out. Give me 1 second, everyone. Do apologize. This is the only way I can sort of share my iPad onto my computer because Apple doesn't have an innovative way of actually doing it. Don't know why it does that, Apple. All right, there we go. That was what I was trying to show you all. Let me move this back down to where it was before. There we go. Apologies. Then we have our PO4 3-. So our PO4 3-, as you can see here, we have an overall charge of, -3, and we've got oxygen, which is -2, and we've got 4 of them, so it's going to be -8. So -3, -8, what's the difference? It's 5 is the difference, so this is going to be +5, and therefore this is going to be +5. Now, I get rid of all of that again, and then I go through and I go like this. You can see it's all there. Again, if it wants to load. Moving forward, they have H3O+, which we already just went through. I don't know why this is completely lagged out. I do apologize. Let me just keep doing this. If this continues to happen, I'll just change how I'm going about it, everyone. Sorry. I do have a cord here to be able to connect them. Sometimes it just happens to do this. The joys of Apple. But we've already been through this example, so we can just push through this one pretty quickly. All right, very good. So, how do oxidation states allow us to figure out if a redox reaction occurred? So, what we need to do is we need to find the oxidation state. So let's go through and have a look at the oxidation states of everything here. So, what I've got here is I've got +2. What I've got here is -1. What I've got here is +2 and -1. What I've got here is +1, -2, +1. I've got +1, -1. I've got +1, -1, +1, -2. I have 0. I have 0. I have +3, and I have -1. So, which of these is redox? For those of you who've never been through redox, you're going to have no idea. You're going to be sitting here like, how is this useful? What is going on? That is completely fair enough. As you have been through any redox, you would know by looking at this, which of these is redox? Well, it's the one with change. So which of these has change? The one that has change? Number 3. So going through it. Not redox is the first one. Not redox the second one. Redox the third one. So in the first two, there is no change in oxidation state. What that says to me is there's no movement of electrons. Electrons have not moved. So in these ones here, there is no electron movement. With no electron movement, this is not redox. In this last one, because there is significant electron movement, this is redox. It doesn't even need to be significant, just any movement. So a reaction will only be redox if 2 or more atoms have a change in oxidation states. Really important, it needs to be 2 or more, but there's always going to be 2 or more. Like you're never going to be provided one with 1 or more. With 1, sorry. If the oxidation state reduces, then the species was reduced. So which of these was reduced here? Have a quick think. 3, 2, 1. It's the chlorines. So the Cls are reduced. And if the oxidation state increases, which of these were oxidized? Well, I don't even need to make you think because it's just the other one there. The aluminiums were oxidized. And it makes sense. Oxidation involves loss. Losing electrons means you lose negative charges because electrons are negative. So losing negative charges means your oxidation state should go up. Your Cls have gone down because they've gained electrons. Reduction involves gain. Gaining electrons, reduction, and you're going to have a decrease in your charge because you're gaining negative ions. So that's how that works there. So I want everyone to have a sort of a go at this question. Essentially, for those of you watching the live stream, I'm going to give you sort of 20 seconds just to think about this question. For those of you doing the recording, please feel free to just pause this and have a go. But this is a really good question that I want sort of everyone, including those watching the live stream, to do. So I am going to wait sort of 20 seconds. What happens to Fe2+ in the following reaction? Have a quick think. I'm going to give you 20 seconds. You can see at the top, we've got 20 seconds from now. Go. 24 past. We're going to do it. So 10 more seconds. And done. All right. That's a very short amount of time. You'd obviously have way more time, but given we're doing a recording, I don't want to waste too much time. So what happens to Fe2+? Well, what have we got? We've got an oxidation state of +4, +2, +3, +3. So we've gone, Fe has gone from +2 to +3. Going from +2 to +3 means that, or what has occurred, we've had a gain of charge, but a loss of electrons because we've lost an electron to gain a charge. So therefore we've lost electrons, has to be one of these two, process elimination, C or D, and then which involves loss? Oxidation involves loss. Therefore the answer here is C. This is a pretty straightforward type question, but it's a really good question to start off with. This is a really good question as you're starting off redox because it sort of goes, all right, really basic concept. How do I go about it? What's my technique and my approach to a question like this when it's just the basics? This is a really good one for it. It involves oxidation. It involves loss. Has to be C. It's not going to be A, B, or D. So the overall redox reaction, as you can see here, we've got magnesium solid plus oxygen gas goes to MgO, can be split into 2 half reactions, which show the electrons moving. Remember oil rig? There are 2 half equations. We have oxidation and we have reduction. Remember those general formula that I showed you? The general formula all the way back here. Remember these? These are what we refer to as half equations. Now, half equations are really, really important. Half equations are theoretical ways of saying what's going on. Half equations in in actual actual sense, like in the actual reaction and in the real world, don't occur. We can't pull out a half equation from a full equation and say, all right, a half reaction. We can't even pull that out and say, all right, we just want the half reaction to occur, and then make some like vacuum where we just have the half reaction. It's not possible. Because why not? You need to have reduction and oxidation at the same time. So you're only ever going to see, when you do a redox equation in real life, you're only ever going to see the whole equation. That's all you're ever going to see. But we know that deep down what's happening is there's two half reactions occurring that form this one big reaction, which is all we see. So in this case here, our oxidation reaction would be Mg solid goes to Mg2 plus 2E minus. Because if we think about it, this was 0, and then this is 2 plus. So going from our sort of Mg0 to our Mg plus 2, and then here we have 0 and we go to -2, this has lost electrons because we've gained charge. So oxidation involves loss. Therefore, we're going to say, all right, the electrons are on the right side because, they're heading off. They're gone. But they're not actually going to head off. Where they're going is they're going here. That's where the electrons are going. The electrons are moving down there. And when they move down there, what you see is that you get this electrons moving down, and you get this. I don't know why this is wrong, first of all. This one is wrong, by the way. Let me fix this second equation here. I don't know why this one is really wrong. But this is going to be O -2, and this is going to be, I believe it's going to be aqueous, and then this should be 2. This half equation down here is just wrong. I do apologize. But that is what it's going to look like there. So you're going to have the electrons actually flow around into here. And that's where that's going to go. So what is the best way of looking at these and learning about these half equations? Well, the best way of looking at these, because that one was really wrong, is going to your electrochemical series. Now, this will probably be the first major use of your chemistry data book that you're going to work with, because it's sort of the big hit the point, hit the mark sort of thing that you're going to do. So if I scroll down to page 4, so it's one of the first couple of pages, you find figure 2 electrochemical series. So the electrochemical series essentially has all these numbers here, which I don't want you to worry about for today. But the numbers we will talk about or you will talk about in class, and we will talk about it in our next set of lectures in spring. For now, these are not super relevant to you because they're sort of the next step on. So we're not going to worry about the numbers. What we're going to worry about is all of these half equations. As you can see here, these are all half equations. Now, all of these half equations are in the form of what's going on here. We're gaining electrons, so they're all reduction because we're gaining electrons. These are all produced as reduction equations. We can flip these and put like the Ni solid here, and then Ni2 plus 2E minus, and then therefore this would be oxidation. But they're all produced as reduction equations, so that would be oxidation. They're all reduction equations for now. So don't worry too much about it. These are just all oxidation equations for now. So in looking at that, what's going on here and why is the electrochemical series in this sort of order? So the electrochemical series is kind of cool because it is sort of different elements looking at how they react together. So we all know that things react differently. And so what we do is we rank elements based on how easily they oxidize or how easily they reduce. And we can look at that through our numbers. I don't want to worry about the numbers today. What I want to worry about is saying, all right, where are our strongest oxidants and where are our strongest reductants? Because remember we say the oxidant causes oxidation in our other species. Our reductant causes reduction in our other species. So if they cause it, which ones are the strongest oxidants and which ones are the strongest reductants? Which are the ones that are going to cause it more? It's like our sort of acids and bases, how we have strong acids, strong bases. They're more likely to accept or more likely to donate. Same thing, but here it's more likely to cause reduction, more likely to cause oxidation. Those concepts. So where are our strongest oxidants and where are our strongest where are our strongest oxidants or where are our strongest reductants. So given that this is a redox equation, and this molecule here is going through redox, so this one here is going through redox, what do we think? Is this going to be an oxidant or a reductant? Because it's going through reduction. So have a quick think, is this going to be an oxidant or reductant? It's going to be an oxidant. So this here is going to be an oxidant. And what I will tell you is that this is the strongest oxidant. Down here, this is the weakest oxidant. So what we can say, coming back to this page here, is that this is oxidant strength. So if that there is oxidant strength, which way do you think reductant strength goes? Given that these now on the other side are reductants. Well, if this down here doesn't want to go through oxidation, it's actually going to really want to go through reduction. So this is reductant strength. So oxidant strength goes up, reductant strength goes down. So there are other things on this I really want you to label. So the other things that I think are really key for us to label here today are our standard hydrogen electrode. Now, standard hydrogen electrode falls at 0. Now, just for context, this whole chemical series was made under SLC conditions, which we'll discuss in a second, and it was all made based on standardizing from here. So these values, these number values and everything that's sort of put in the order it is based upon how it reacted with the standard hydrogen cell. So the standard hydrogen cell is given 0 because it was the standard, it was used in the middle. The strongest and weakest oxidants, this is the strongest, this is the weakest. The strongest and weakest reductants, this is the weakest, this is the strongest. And then if you look through, there are a few other things that you could label, but I think for now this is all we really need to do. So this is a really cool series. It's really useful, and you'll be able to use it in questions. We're probably not going to go through how you sort of utilize it fully in questions today. We're going to discuss it very briefly, but this is what you're going to use in a lot of your questions. So it's good to be familiar with it and familiar with how it sort of is set up, because it's set up in a very, very specific way. So looking at this, just quickly, because we did discuss this, SLC conditions. So SLC conditions are what we refer to as standard laboratory conditions. These are a set of standard conditions to ensure we control all potential variables. So these include having whatever you're doing at 25 degrees Celsius. Also could be referred to as 298 Kelvin, because Kelvin, degrees Celsius, we know all about that now. If it is a gas, it needs to be at 100 kilopascals of pressure. So that is just a measurement of pressure. You need to be at 100 kilopascals. If it is a solution, it needs to be at 1 molar concentration. So what we're doing here is we're just trying to standardize. Think of a bit of experimental design. All we're trying to do is say, hey, if we make everything as sort of standard as possible and we minimize the potential sort of reactions that could occur, if we standardize things as best as possible, this is what we get. So if these conditions are not met for the redox experiment, we cannot utilize the electrochemical series. Really, really important. So if a question doesn't have everything at this, we cannot use the electrochemical series. So let's apply the concept. So we will do one little application of it. I want everyone to write out the half equations for the oxidation of zinc to zinc 2+, and then the reduction of Ag to Ag solid. So Ag plus to Ag solid. So for those of you who are watching the recording, please pause and have a go. We're just going to go jump straight into it. So I could go ahead and do this because they're fairly straightforward concepts. We have zinc solid, and it's going to zinc 2+ aqueous. So where do I balance? Well, this is +2 and this is 0, so I'm going to add 2 electrons here. So what have we got? It's losing electrons, therefore this is oxidation. Happy with that. But there's an even simpler way of going about this. Most of these simple half equations are found, just here. Most of them are found in here. There is my zinc half equation. I just have to flip it around. The other one we were working with was Ag. Ag is up here at the top. Ag is just here. So I just need to copy that down. And because this one is actually going from Ag plus to Ag solid, unlike the last one, this one I can just copy straight out of the book. So goes Ag plus aqueous plus E minus. Now electrons don't have a state, really important, so don't put a state with them. Goes to Ag solid, and that was oxidation, so this is going to be reduction. So really important you sort of understand that you can use the electrochemical series to sort of obtain this information that may seem like these may seem like a little bit difficult at the start, but you can just go to electrochemical series and most of the time your answer's there. Now, the next step here is write the full equation. So how am I going to go about this? What is going to be involved in writing my full equation? Well, I need to add these two together. So I need to add them together. By adding them together, I need to eliminate my electrons. What's really important here is that this is 1 and that is 2. So I'm going to need to double this equation. So it's going to need to be 2, 2, 2, and 2. In doing that, that goes and that goes. They balance each other out. So my overall equation is going to be zinc solid plus 2 Ag plus aqueous goes to Zn2 plus aqueous plus 2 Ag solid. And that there is my full redox equation. That is what's going on there. So, as you can see here, I've removed my electrons by doubling the bottom equation. I've removed them because they cancel each other out, and then I have my full equation here. So, the last little concept, there's like 2 little concepts I want to go through before we finish off, and that is our production of half equations when they're not in the electrochemical series. So, when our half equations are not in our electrochemical series, things can seem a little bit difficult. You might get to the question and be like, oh lordy, what am I doing? This doesn't make sense, what's going on? I've checked my electrochemical series, I go here and I scroll through, I'm like, oh, I can't find it here, what's going on? Why is this so difficult? That's because they're expecting you to create it, and sometimes they do expect you to create it. So, how do we actually figure out the half equations if they are not in the chemical series? We use this method called COES. Now, COES stands for, each of those letters stands for something. So we have like key elements, oxygen, hydrogen, electron states. So they each stand for a step. Now, the COES method involves 5 steps. Step 1, balance the key atoms. So realistically, the first step is to write down what's going on. So write down, what do you start with, what do you end with? Because that's what you're going to be given. You're going to be given, hey, this ends up in this, right? This is a half equation, like a half redox equation. And you're going to be like, I know this gets to this, but then what else is there? Where are the electrons? It's not showing me on the electrochemical series. What do I do? Go ahead and do the COES method. So K. K is your key atoms. So all atoms except for hydrogen and oxygen need to be balanced first. So you need to balance them out. Second, balance your oxygens by adding H2Os to the side where there are less oxygens. So if you've got 2 oxygens on one side and no oxygens on the other, you're going to need to add 2 H2Os to that other side. The third step, balance your hydrogens. Now you balance your hydrogens by adding H+. So if there are 2 hydrogens, so maybe you added in 2 H2Os on this side because you had to balance out your oxygens, you now have 4 hydrogens here and you've got 0 hydrogens on this side. You're then going to have to add 4 hydrogens on this side because you have 4 here, so you need to add 4 H pluses here. You then add your electrons by balancing your charges. So you've gone and added H2Os here, which made you add hydrogens here. You added 4 of them. You've got 4 H plus here now. There's no other charges within this half equation, but you've got 4 H plus here. Therefore, you've got a charge of +4 here. You need to, and a charge of 0 on this side. You need to balance that out by adding 4 electrons to this side. So you go 4 plus to 0. And you go 0 to 4 plus, you add 4 electrons, you go from 4 plus here to 0 here. Lastly, you just need to don't forget states. You just need to add in states. So you might see me at times forget to put states in. That's just because we're obviously not an exam or a stack right now, so I'm probably a little bit lazy in putting my states in. But it's really important to get into the habit of putting states with everything, because once you get to exams and sacks, it's really important you do put states in. If you continue to forget, you're going to continue to lose marks. So really important you go through that. So the best way to learn the COES method is to go through an example. So we're going to slowly go through this example. For those of you who are at home, please have a go at this first. Please pause this video and just have a go. The first thing, well, before you pause, the first thing you're going to do is you're going to write out your atoms first. So you're going to say SO3 2 minus. Now give yourself some space. So give yourself some space and then write out SO4 2 minus. So you've given yourself some space. You've got space here to write and space here to write because you may have to put something in there. From here, I want you to have a go at this question. Use your COES method. Think of each of your steps. Go, all right, I've got K, and then O, and then H, and then E, and then S, and go through each of these steps. So I want you to take your time and go through this question. So those of you at home watching the recording, please pause now. Those of you in the live stream, you're welcome to head off and have a go at this and then come back, but we're going to go through it right away. So start off with K, key elements. So what are our key elements here? Well, sulfur is our only one, and there is one sulfur on either side, so we don't need to balance. Cool. We can actually skip that step. 2, oxygen. Need to balance my oxygens. I have 3 here and I have 4 there, so I'm going to need to add 1 H2O here because I've got 2 on this side and I've got 1 on that side. So sorry, I had 4 on that side and I had 3 on this side. Therefore, I need to go from 4 to 4. I now have 4 and 4. Now I need to balance my hydrogens. So I added 2 hydrogens into the left. I've got none on the right, so I need to add 2H+. Now I need to balance my charges. So my electrons, my E. Balancing my charges, I've got -2. I've got -2 plus 2, so I've got 0. I need to add -2 to this side, so I'm going to need to add 2E minus. That is my overall equation. But remember the last step. Last step's one of the most important ones. Don't forget the states. So I don't want to forget the states here, so I'm going to add in an S, and I need to add in my states. So this will be aqueous. If you're not sure, it's always going to be aqueous. This is liquid. This is aqueous. This is always aqueous, and there's no charge, there's no state on your electrons. That is your overall equation. So we have just been through the COES method, and we have just produced a half equation for this example here, which, if you go to this, it's not here. And the other really cool tip here to check that this is right is, if I look, I've gone from, this is -2, and this is -2, and I go, all right, this is, sorry, just get rid of these scribbles. So back to this, I've got -2, I got -2, therefore this is going to be -6, and it equals -2. I need this to be +4. Here, this is -8, and this is -2. So therefore I need this to be +6. So I've gone from +4 to +6. So +4 to +6 here. So where are we? We're at +4 to +6. +4 to +6. That is a loss of electrons. So it is oxidation. Oxidation involves loss. Oxidation has its electrons on the right because it always loses your electrons on the right. And as you can see, the electrons here are on the right. So it's another quick way of saying, all right, did I actually get this right? Did I do this half equation right? Well, I did because my electrons are on the correct side. And that's like a good sort of second step to figure out if you've done everything correct. Now, we have talked about acids and bases. And what about our initial COES method was acidic or basic? Have a quick think. 5, 4, 3, 2, 1. What do you think? What was acidic or basic about it? Well, it had H pluses added in. When you add in H pluses, what have we got? We got an acidic compound. we got an acidic solution. So the Coase method, we have been making an assumption that the reaction medium is acidic. Now, you are going to make this assumption no matter what if you are not told in a question if it's acidic or basic. So if you're not told in a question that your solution or your medium is acidic or basic, you assume it's acidic. You assume H pluses. Really, really important. You assume acidity. But what if instead you are told, and it's really important, you will be told the reaction medium is basic or alkaline. We need to add in an extra step. So we have our normal Coase method, which we've already been through. We add in an extra step. That extra step is adding in OH minus ions. So we cancel out the hydrogen ions by adding in OH ions. And this complicates this. So let's jump back to this example here. Let's go back through and get back to our K. So we're going to go back to this example. We're going to do this example again. And we're going to get rid of this. And we're going to do this example in orange. We're going to say, all right, SO 3 to negative goes to SO4 to negative. So we're going to do this example again. This example is going to look like this. Again, balance our key atoms. Cool, we don't need to. Oxygens next. So add in our oxygens. H2O, cool, happy with that. Balance our hydrogens. Plus 2 H plus. Cool, happy with that. Extra H. So we've been through step 1, which was our K, step 2, which is our oxygen, step 3, which was our H. Now we're going to step 4, which is our extra H. So at this point, we're at our extra H step. There's our extra H. We need to add in hydroxides. Now, how many hydroxides am I going to be adding in? Because I want to balance this out. Well, I'm going to be adding in 2. So I'm going to be adding in 2 OH minus, and I'm going to be adding in 2 OH minus. You need to add it to both sides here. You can't add to one side because you're not balancing. In this one, you're neutralizing or cancelling out. By cancelling out, you need to add one into both sides. When you're balancing, you can just add to one side. This step, we're not balancing, we're cancelling out. Really important wording, as you can see here, really important wording. Balance, 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 balance. And these ones you can just add to one side and not add to the other. This step here is cancel, so you have to add to both sides when you cancel. So coming back, we have SO3 plus H2O plus 2 OH minus, and we have SO4 2 minus plus 2 H plus 2 OH minus. Now, how do these cancel out? These cancel out by going bang, bang, plus 2 H2O. So now we have H2Os on both sides. Well, that's a bit useless. By having 2 H2Os on both sides, we then need to cancel out again. This goes and it becomes +1, and this one goes. Then what we need to do is go back to our equation and go, all right, we've done our extra H, now we're on to E. Electrons. Now, what do I have? I have a charge of -2. I have a charge of -2, -2, -4. I need this to get to -4 on the right side here, so I'm going to add another -2. By adding another -2, that is going to come from 2E minus. Now, then you go ahead and add your states. So this is going to be aqueous, 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 and liquid. The one thing that's really important about this method is if you've already done the acidic one and then you go and do the basic one, you need to make sure that you have the electrons in the same place, and usually it's the same amount. So same amount, same place. They're both on the right side. There's still oxidation, and you still have 2. Tick, that means I'm comfortable that I've done both my acidic and basic techniques correct. So I've correctly been able to adapt my acidic technique into a basic technique here. So that's a really key concept to be able to do. So Coase, acidic, you assume acidity unless told otherwise. So if your question doesn't mention an acidic environment or a basic environment, you do Coase without the double H. You do the acidic version. Acidic is your base. You always, well, it's actually a really bad way of saying it. your acidic is your fallback. It's your standard. You're always going to do acidic unless you are told it is basic or alkaline. If it is basic or alkaline, you add in the extra step. So, moving forward, just quickly, this is like the last concept. We have 2 slides left and then we are done. So we've probably got about 5 or 6 minutes of just these last 2 slides and then we are done. So, as you can see here, this is just quickly our electrochemical series, and with this we have a reaction that will occur spontaneously if the oxidant, so the left-hand side, is above the reductant. So this is sort of the last concept. Redox only happens if it's spontaneous. Now, if you have non-spontaneous reactions, so you're forcing reaction to occur, this is electrolysis, and it's what you will talk about in year 12. So please don't worry about it for this year. This year, everything has to be spontaneous. And for something to be spontaneous, it needs to be left-hand side to right-hand side. And it needs to be top left to bottom right. So, as you can see here, I have an equation here that says Zn solid plus Cu2 plus goes to Zn2 plus Cu solid. This is a redox equation. This redox equation is spontaneous because, what have I got? Top left, so I've got a strong oxidant. Bottom right, I've got a strong reductant. That's why we think of it like that. It's top left, bottom right. Strong oxidant, strong reductant. Strong oxidant, strong reductant. Now, if I were to use this equation here, so going back, I've got Zn solid plus Mg2 plus goes to Zn2 plus Mg solid. This is also a redox equation, but as you can see here, my Mn2 plus is below my Zn solid. So I've got, not only I'm looking the other way, I've sort of got a weak oxidant and a sort of a weak reductant. Like it's not going to work. So this is not spontaneous. This will not work. So it's really important to understand that when we look at redox and we look at overall reactions, they only occur if you've got a top left and a bottom right. Really important. For spontaneous reactions to occur, it is top left to bottom right. Top left to bottom right. It's the same as what we think about with our oxidants and reductant strength. Top left, bottom right. So always think of it like that. Top left, bottom right, top left, bottom right, top left, bottom right. For spontaneous reaction, which is what you're going to work with this year in redox reactions. So there's a really good question for this, and I want everyone to sort of take their time to have a go at this. So for those of you who are at home, I want you to pause this video and I want you to go through this question. Now, this is a 2-mark question. Think about where your 2 marks are. Think about how you're going to get your 2 marks. For those of you in the live stream, I want you to take 30 seconds just to think about how you would answer this question. I don't want you to write it down or anything. You're not going to have time. I just want to give you 30 seconds. So starting from now, 30 seconds, think about how you would answer this question. What are the steps you would take? And that should be your 30 seconds. So hopefully you had enough time to sort of think about it. So what I would have wanted you to do in that 30 seconds is identify whether this is yes or no. Because if you just identify what we've got at the start, you've got Br2 and you've got Cl minus. So straight away, you should have just been able to identify in those 30 seconds that the answer to this is no. And then where are my 2 marks? How am I going to get my 2 marks? This is the big skill I want you to work on in this semester heading into year 12 is how to get your marks from questions. It's a skill, and it's particularly in science subjects like chemistry, biology, physics, those 3. How do you get your marks? Psychology is a little bit different because it's very much more like the way you need to answer questions in psychology is more like a humanities arts, whereas things like chem, biophysics are very similar in how they want you to answer things in a very scientific approach. Psychology is more about discussing what could be and what couldn't be. Science, you discuss, yes, it is, no, it isn't. So like our chemistry, biology, physics, you discuss whether it's yes or no. In this one here, you're going to say no. How am I going to get my 2 marks? My first mark in this one is essentially going to be if I get it right. Is it yes or no? Well, will it be a spontaneous reaction? It will not be a spontaneous reaction. Full stop. That is the first thing I want you to do. That is the first thing that happens. That is the first thing overall. It will not be a spontaneous reaction. That is your first mark. Where is my second mark coming from? My second mark is going to be coming from this. Justify your response. They want you to justify it. Why? So we're going to use chemical concepts here. Your chemical concepts are that chloride ions are a stronger oxidant chloride ions. Let me reword that. Chlorine gas is a stronger oxidant than bromide liquid. Therefore, this reaction would be non-spontaneous. Now, the key concept in this question is you shouldn't really compare an oxidant with a reductant. You shouldn't say chloride ions are a weak reductant, and then bromide liquid is also it's a weak reductant and a weak oxidant. So therefore, these things are not top left. These are not top left, bottom right. They're actually bottom left, top right. You should be comparing oxidants with oxidants and reductants with reductants. So you want to say that chlorine gas, which is your pair, your conjugate pair there to your chlorine ions, is a stronger oxidant than bromide liquid, and therefore it would be non-spontaneous. The other thing you could probably talk about here is electronegativity. If you wanted, you could say that given this, chlorine is going to be a more spontaneous, a more electronegative molecule than bromide liquid, and therefore you're not going to get that that interaction. I probably should say bromine liquid, not bromide liquid. That's actually wrong. Apologies. Bromine liquid. But that's something you could talk about there as well. So they're the concepts there that you need to go through. So in summary, what we've been through today is we've been through most of Area Study 1, tiny bit of Area Study 2 for Unit 2. You've really gone through acid bases and everything to do with water and acid bases. We've gone through the basics of redox. What's really important about all of this is that I don't want you to come out of today and be like, I'm an expert at redox, because you're not going to come out of today as an expert at redox. What you're going to come out of today is some of the basics. And then next time you go through redox, you're going to be like, oh, cool, I'm on top of that. Same with acids and bases. Although today should cover most of it and you should feel pretty comfortable, there are some little areas we didn't because of time constraints. So therefore, you should come out of today feeling pretty comfortable to go in and not be pushed by any acid-based questions or any new concepts for acid bases, because you know the building blocks of it and the water and all of that. Otherwise, that's everything for Chemistry 1-2 for this lecture. Hopefully that helped, and we will be running these lectures again, and there'll be a fresh recording with new concepts and more exam-style questions in the spring break. Other than that, good luck for the rest of the year. Hopefully I'll be seeing you again, and enjoy.